Hello, everyone. I wanted to make a video for you for the beginning of section 2.6. Um, section 2.6 is all about the squeeze theorem and trigonometric limits. I want to spend our class time on the trigonometric limits because those are the things that you're going to be tested on, and I'm going to need you to kind of start wrestling with. There's only one squeeze theorem problem in your homework. And so I wanted to be able to spend class time on the things that are really going to matter for you. So this is going to be a quick video to help you with that squeeze theorem problem in your homework, and give you an idea of what the squeeze theorem says in case you see it in some of your other classes. Okay, so the squeeze theorem. This starts with the fact that we have a function that is stuck between two other functions. So let's say f of x is always between L of x and U of x. We use L and U because L of x is going to be our lower function and U of x will be our upper function. Okay, so just to give you an idea of what this might look like, I'm just going to draw some functions here for you to give you an idea of what I mean by this. All right, so let's say L of x looks something like this. This is our function L of x, and I'm going to need L of x to be underneath the function f of x everywhere, less than or equal to f of x everywhere. Okay, and then we also have u of x. So u of x is going to be an upper function. So that's going to be above my function f everywhere. So I'm just going to draw a function up here. This is u of x. And basically what we're going to need is that f of x has to stay between these guys. So L of x is always less than or equal to our function f, and u of x is always above, greater than or equal to f of x everywhere. And so basically what this means is that f of x is going to be stuck between these two functions. There might be places where we touch the other functions, pretend that these actually touch and that these actually touch. So we can touch these functions, but the function f can't cross to the other side, right? That red one has to stay above or equal to the blue one, and that green one has to stay below or equal to the blue one everywhere. So our function f of x is this middle one. Okay, if we have this current situation, then what happens if there was an x value? We're going to call it x equals c, where the limit as x approaches c of my upper function, my top function, is equal to the limit as x approaches c of my lower function. And that equal limit we're going to name L. So what would that look like? Okay, so let's draw this a little bit. Actually, I'm going to start with the red one. All right, so we have our upper function, right? I don't know, it's going to look something like this. There's our u of x. It's our upper function. And I know that, let's just say x equals c is right here. The limit as x approaches c of u of x equals L. So this y value here is L, right? That's the limit as x approaches c of u of x. But that value L is also the limit as x approaches c of L of x, my lower function. So what that means is that L of x is stuck down here. It also has to have a limit of L at x equals c, right? That's really what this is saying, is that the limit as x approaches c of my upper function is exactly the same as the limit as x approaches c of my lower function. Okay, so that's the situation that we're in here. What does that mean for my function f of x that's stuck between these? Well, f has to be between the red and the green function everywhere, so I'm going to have to draw this here. But what has to happen at x equals c? Well, if I have to stay between these guys, I have to go through that same point as well. What that means is that the limit as x approaches c of my middle function also has to be L. These upper and lower functions are going to squeeze my middle function together and force that limit to match the limit of the other two at the same spot. Hopefully that makes sense, right? We're just saying that, yeah, if you have a function that's always above or below, and they have the same limit at the same point, they're going to squeeze that middle function and force it to have the same limit there. And this very special case is what the squeeze theorem says. It says that those upper and lower functions, if they have the same limit at a c value, they squeeze that middle function and force it to have the same thing. So if for x not equal to c in some interval containing c, if we have that L of x is less than or equal to my function f of x, and that's less than or equal to u of x. This is basically the situation that we set up here, saying that u of x is that top function, L of x is that low function. As long as we have that situation, and we have the limit as x approaches c of my lower function is equal to the limit as x approaches c of my upper function. And again, I'm going to call that limit L. That's where we started in this situation here. If my upper and my lower functions have the same limit at x equals c, then I know that that's going to force the limit as x approaches c of my middle function to exist. And I know what that limit is. It's going to be L, just like my upper and my lower functions. So this says exactly what we noticed up here. It just puts it into mathy language. Okay, so as long as we have, if we have a place where the top and the bottom functions have the same limit, it forces the middle function to have that limit as well. The main place that you're going to use this theorem is with sines and cosines. The reason that this function is so helpful with sines and cosines is because of this fact right here. We know that sine and cosine are bounded functions. They're bounded above, they're bounded below, right? The sine of x, that is stuck between y equals -1 and y equals 1 everywhere. I have an upper and a lower bound. And the cosine of x is also stuck between 1 and -1 everywhere, right? Because these functions are waves like this. And so they are generally stuck between my lower function, y equals -1, and my upper function, y equals 1 everywhere. That's what this is saying. Right, and that's something that we hopefully have observed before. And the cool thing about this is that even if you don't have just an x in here, if you have a whole function in there, if you have like the sign of some stuff in there, so like if you have the sign of x squared plus 1, or if you have the sign of e to the 2x, if you have any function inside the sine function or the cosine function, it's not going to change the fact that this is bounded above and below by -1 and 1. If you want to, if you don't want to hit the I believe button on that, go ahead and go to Desmos. If you've never been there, you go to www.desmos, DESMOS/calculator. And it's an online graphing calculator. And you can just graph whatever you want. So you can graph y equals the sine of e to the 2x and see what it looks like. You'll notice it's also stuck between y equals -1, and y equals 1. And then change the stuff in here. You can put any function you want in there. Play with it and see what happens to your sine function, but you will notice it is always stuck between -1 and 1. So that's very cool. And whether this is sine or cosine, that's going to be the case. So this is kind of where we're going to start. So the way that we use this is that if we wanted to evaluate the limit as x approaches 0 of this lovely function, x times the sine of 1 over x using the squeeze theorem. Okay, if I plug this in, if I, where we start with limits, I always want to just plug it in first. If we start where we always do, I get 0 times the sine of 1 over 0. Yeah, I don't, 1 over 0, that's a vertical asymptote inside here. That's heading toward infinity or negative infinity. I don't know what the sign of infinity or the sign of negative infinity is. I can't do that. So I can't evaluate this directly. That is not going to work for me. So we have to come at this a different way. And so basically where we're going to start is right here. You're going to take the sine of the stuff that you have in your problem. In our case, I know there's an x out here. We're going to deal with that in a minute. Ignore that for the time being and just start with the sine of whatever is inside your sine function in your limit. We're going to start with this. If you had something other than 1 over x in there, this would just be whatever is inside your sine function in your original limit. Now, this is the sine of some stuff. I know that the sine of any stuff is always stuck between -1 and 1. So I can start with this. I know I have an extra x there. I'm going to work on that in a minute. But to start with, you just start with the sine or the cosine of the stuff that's in there and stick it between -1 and 1. But this isn't the limit that I want. I want to know what x times the sine of 1 over x does. So what I'm going to do now is I'm going to play with some algebra, and I'm going to try to make what's inside here look like the full limit up here. So now, in order to make the middle look like what I've got, I have to multiply that by x, right? To make it look like what I've got. So I'm going to multiply this by x. But if I multiply the middle part of this by x, I have to multiply everything by x, right? I have to multiply this by x, and I have to multiply this by x. And from there, now I can go forth. And so once I multiply everything by x, I'm going to get negative x here is less than or equal to x times the sine of 1 over x, and that's going to be less than x over here. Notice that now this middle part matches what I started with, and I wanted to know what the limit of this middle thing was. Okay, well, now that we have, sorry, I keep trying to switch colors. I'm gonna come to black now. Now I have a function that is a, oops, sorry. Now I have a function that is a lower bound for my f of x, and I have a function that is my upper bound of my f of x. And notice that the limit that I want, the limit as x approaches 0, notice that the limit of my lower function at that x value is 0, and the limit as x approaches 0 of my upper function is also 0. Right? So the limit as x approaches 0 of my lower function and the limit as x approaches 0 of my upper function is the same. So these two functions are going to squeeze this middle theorem, and it's going to force the limit as x approaches 0 of x times the sine of 1 over x to also be 0 by the squeeze theorem. So this is really how we use the squeeze theorem, And your process for any of these functions is going to be the same. Start with the sign of whatever stuff you have in your numbers here. Just deal with that in a minute. Kind of ignore that at the very beginning. Just take the sine or cosine of your stuff, whatever that is inside your limit, and start with that and bound it between -1 and 1. And then from there, you're just going to multiply everything in your function by whatever you need to transform the sign of your stuff into the entire limit that you have. So if we had like a 3x squared out here instead of an x, you would multiply everything in your function by 3x squared. If I had the sine of 1 over x divided by -2x, then I would divide everything in this equation by -2x, and then evaluate the upper and the lower function at this x value. Take the limits of both, and as long as they match, they will squeeze that middle theorem into the same limit. Okay, I hope that helps you with the squeeze theorem part of your homework. And I will see you next time to work on section 2.6, the trigonometric limits in class. Have a great day.